Great. So I think we're about to hit the 1 o'clock deadline. There we are. Nice to see everybody. And it was very exciting to start this new series, Wonders of God's World. And this is part of the Mary Heiken DUMONT University here at Anshei Sphard Beth Emeth Congregation, or here on the Zoom world in the Netherlands of Zoom world. The idea of the Wonders of God's World as part of a synagogue series may seem strange to some people. Why are we talking about astronomy and DNA and the workings of the brain at a synagogue or even on the Zoom channel of a synagogue? And the answer is very simple. And that is that part of our work as worshipers of God is to appreciate nature. Hallelujah, Hashem Hashemayim, Halu B'Amromim. Every morning we say, Hallelujah, praise the Lord from the heavens, praise Him from on high. If we fail to appreciate that aspect of God's creation, namely the universe itself, and also the wonders of the human body, whether it's DNA, whether it's the workings of human brain, then we fail to praise God from the heavens and from the earth. And of course, the Rambam in the beginning of the laws of Deot, of personality and character, he says that how do we come to love God and fear God? And that is when we begin to think of all the wonders of God. We see the wisdom of God, which has no end. We begin to immediately love God, and then we realize how magnificent and how expensive the universe is. We come to fear God as well. So, as non-scientists, as some of us are, we need a little help from the scientists among us in order to appreciate nature and in order to really worship God out of fear and of awe of His creation. So we call on Gabi. Gabi is Gabriella El-Kaim. LaVene is married to Charles LaVene. Some of you may know from our community. And he had his bar mitzvah at our shul. His grandmother was Shirley Bluestein. She was very beloved in our community as well. And she has a degree in physics from Yeshiva University and is a real science aficionado and a lover of science. And she often lectures about astronomy as well. So we're looking forward to her talk today. We thank her for joining us. Very much appreciate sharing her time with us. We thank each one of you for joining us today. So this time I'll turn it over to her, and let me spotlight her video as well.
All right, thank you so much, Rabbi Finkelstein. And just at risk of misrepresenting myself, I want to make it clear, I'm not a professional astronomer. I do have a degree in physics, but I don't work professionally in astronomy. I'm very much an enthusiast. So I have fact-checked everything here, and I'm giving you accurate information, but I don't want to present myself with more expertise than I have. So that being said, when Rabbi Finkelstein asked me to do this lecture, he said that he wanted to do a lecture kind of focusing on understanding the world at different scales. So I thought maybe I could give a lecture just on the scale of the universe, understanding how big it actually is. And then I realized that that's basically just a lot of numbers, and I don't think that's very engaging, and I don't think it gives a really good idea of the magnitude. I don't think you get a feel for it if you're just looking at like numbers with a lot of zeros behind them. So instead, I want to talk about some of the largest and kind of most impressive phenomena that occur out in space, and some of the things that when I was a kid really intrigued me and really got me very interested in astronomy because I thought they were just so engaging and interesting. And we are going to talk about that idea of scale, of kind of looking at things and comparing their sizes to appreciate how big they are. But I'll wrap that up in part of it. So I guess my first question, I always like to begin with a question, is what is the largest thing that you can think of? And can I just ask, can people see my screen? I prepared a set of slides so that we could kind of see. I wanted to share it. No, space is very beautiful.
Yes.
You can see it?
Yes.
Okay. Also, can you hear me very well? Just because I have an air conditioner going in the background and maybe that's creating static. Can you hear me?
Yes.
Perfect, perfect.
Okay, awesome. Thank you for confirming that.
Perfect.
So I'm going to turn this question back to you. What is the largest thing that you can think of? Like if someone says, like, name something big, something really big.
Heaven.
Heaven, okay.
There's a theory that there are 10 dimensions and that the 10th dimension encompasses every other dimension So I would think that's a pretty big thing. But then there's another theory that like dimensions just get infinitely bigger. But I think
So
I like that theory. Are you familiar with that?
yeah, I think you just went all the way to the end of like
Yeah. I'm
cosmological
just
side.
going all out.
All right.
Just,
So I think when we talk about things that are big, things that kind of are in our lives, and that we can kind of visualize how big they are, the first thing that comes to mind is something like the sun and the moon, right? Those are huge. Or planet Earth itself, right? So I want to first get a grip of like how large is the planet that we actually live on? How large is the star that we see in the sky? So how big is actually a star? So here I've got this image, and this is a size comparison. And there's really two types of size that I wanna point out. The first is kind of the volume, how much space something takes up, and the second is the mass. So this is a comparison of the volume, kind of the physical space that things take up, comparing all the planets of the solar system and the sun. And can you guys see my pointer on my screen as I'm moving it around?
Yes.
Yeah, you can see the pointer?
Yes.
So I'll draw your attention. This is the sun, obviously this big one in the middle, and this down here is planet Earth. I had to highlight it in blue because it was almost invisible, right? Just to give an idea of how much larger, if you think about planet Earth itself and how big that is, then you look at the sun, it's already just incredibly larger. And one of the reasons why I want to show you this image is if you look at just the descriptions of how large they are, right? I actually put down kind of the actual number, right? We've got 6, whatever the name of this number is, 24 zeros behind it, kilograms as the mass of the Earth. And when you compare that to the mass of the sun, it doesn't look like a big difference when you're looking at the number. It's like just an extra 6 zeros at the end. It doesn't look like it's that much bigger. But that extra 6 zeros is a factor of 1 million. So that's a million times as massive, which is why I think having kind of the image really, really impresses it. So this is so big that at a certain point, talking about it in terms of kilograms really gets very impractical, right? Because I either have to put 30 zeros at the end of a number, or I have to use scientific notation and describe everything as a power of 10. So I could say it's 2 times 10 to the 30th kilograms. So we're going to introduce a new unit. When astronomers talk about the sizes of stars and other objects, we often talk about it in terms of solar masses. So 1 solar mass is the mass of the sun. So if I have a star that's 2 solar masses, right, it's going to be twice as massive as the sun. So that's just the size of our solar system. I want to also give an idea of the distances that occur, because this is not the real distance between the planets. So here, where is my image? There it is. Here I've got an image, and it shows the distance to scale. I want to make clear the sizes are not to scale. Jupiter and Saturn have been, like all the planets, have been drastically enlarged so that you can see them and appreciate their shapes. But here the distances are to scale. You can see the sun is in the middle, right, where we expect it to be. Mercury, Venus, Earth, Mars, the inner planets, which you can see like are really close together relative to the others, Jupiter, Saturn, right? And as it goes on, these get really far away. So already we kind of need another unit to talk about this. Talking about it in terms of miles or kilometers, we have the same problem. It's just a ton of zeros at the end of a number. And it starts to kind of lose its meaning to us. So the first unit that we're going to use to describe distance in space is called the astronomical unit, or abbreviated as AU. And it's equal to the average distance between the Earth and the sun. That's kind of the measure that we decide to use, is we're going to measure distances relative to how far away we are from our star, right? So if Jupiter is at a little more than 5 AU, that means it's a little more than 5 times as far from the sun as we are, right? Saturn is almost 10 AU. It's almost twice as far as Jupiter, right? So these things get really, really far apart. So we can also talk about when we start to look at even bigger distances, right, the distances within the solar system, we may describe in terms of astronomical units. Outside of the solar system, measuring the distances between stars, it has to get even bigger, right? We're going to talk about 1 light year, and 1 light year is about 63,000 astronomical units, right? If we're measuring those distances, right, it's like each time the scale kind of increases so incredibly, we need to introduce a new unit just to describe it. And then a parsec, have to include that because that controversy with Han Solo and Star Wars, if you guys have seen that. And a parsec is about equal to 3.3 light years. So we've got like some really, really large units just to talk about. So we've seen these size comparisons within our solar system, just to compare how large a star can get, because the sun is not the biggest star out there. Just to show in this diagram, right, the sun is like a dot. It's barely even visible, right? That's 1 solar mass. You can hardly see it. And then we've got some of these larger stars, and you can see one of these biggest stars, VV Cephei. It's incredible how much larger it is. Some stars can be so large, they'll have a diameter that can be measured in astronomical units. So some of these stars, like Betelgeuse, is a star many people have heard of, and people think of it as this incredibly large star, but on this scale, it's kind of on the smaller end, right, at 11 solar masses. Some of these larger ones, they can get incredibly large. I believe there are some that are estimated to be up to 100 solar masses or more. So these stars can get incredibly large. And just to show what that kind of means, that distance of that diameter of 13 astronomical units for a star, this is what it would look like relative to our solar system. So there are stars out there that if you put them in the position of the sun, they would extend past the orbit of Jupiter. And I don't know have any of you ever done any kind of observational astronomy? Like a show of hands, take a telescope. Someone was talking about going out with a telescope earlier.
Yes.
I want you to imagine standing on the Earth, looking up at Jupiter, which is an object that, you know, if you really know what you're looking for, you could probably see with the unaided eye, but definitely with a telescope. You can look at that and see it from Earth, and just imagine a star that is so incredibly massive and so large that its own body would extend all the way across all of that distance. So that is how big stars, I mean, some can probably get even bigger than that. So they're really, really quite big. So how do stars get to be this big, I think is a question. Like, how do they achieve such a large size, and kind of what keeps them there? So first thing I want to explain is many people, stars are very complicated. I'll just start with that. Stars are very, very complicated objects. And we're not able to observe many of them directly. We have a lot of satellites that observe the sun. So most of what we know about how stars work comes from observations of our sun and stars that are nearby us. So here's what we've kind of observed. As a star kind of accretes matter, are we familiar with like gravity and thermonuclear forces? I'll cover it real brief. So like we said, a star has this like billions of kilograms of mass. And as all of that mass kind of congregates on one point, it creates this very strong pressure of gravity pushing down into the core of the star. And that creates, all of that pressure creates heat, and it creates a circumstance, kind of a situation inside the core of the star where there is so much pressure and so much energy that individual atoms can kind of start fusing. So that's when we get like these thermonuclear reactions where you start having fusion in the core of a star, and you're going to have hydrogen atoms fusing with each other to become helium. And that produces a lot of heat and radiation, which pushes outward. So as a star gets bigger and fusion ignites in its core, now it has this pressure of gravity pulling in, it has this pressure of the thermonuclear radiation pushing outward, and that keeps it in kind of a balance, so that the star doesn't just like explode or collapse immediately. And these two pressures, these two forces, are so well balanced in most stars that their lifetime extends for billions of years. Just take the sun, for example. It's estimated to be, I believe, about 5 billion years old. That's an incredibly long lifetime. Pretty typical for a star, though, because these forces are very, very well balanced. One thing I want to point out in this, was that a question? All right. And just because it's going to become important later in understanding other phenomena, I want to point out in this image, it kind of shows how the pressure is greatest toward the center, right? That at the edge of a star, close to its surface, there isn't a lot of matter on top of that pushing down. But as you get to the core of the star, as you get to its center, there's a lot of matter on top pushing down on it, so that creates very, very strong gravitational forces. And at the same time, the core of the star is where all of that nuclear fusion is happening. So the pressure outward is also greatest at that point. So we're going to have this situation where even within a star, there's kind of different regions of what's happening inside it, right? Because the pressure is all in the middle, and there is a lot less pressure around the edges. So that equilibrium can last for a long time. Eventually, what can happen is that equilibrium can break. And that is where things get really, really interesting with astronomy. And I think that's where probably the bulk of a lot of astronomy research and observation is done, is kind of looking at stars at different stages of their lifetime. And particularly examining how long do stars live, how do they die, what dictates how they die and how they live, right? Do stars of different sizes, do stars of different masses do different things? And it turns out that they do. So the first thing that can happen, so this is an image I've pulled up of a white dwarf, which is a type of star. It's kind of a stellar remnant, really. This is the Ring Nebula. And just to illustrate again that point about size, its diameter is 2.6 light years, right? You can kind of see the star in the middle, but it's big enough, right? This ring is large enough that there could be other stars within that space, right? 2.6 light years. That could host another star. Just for comparison, I believe the star that's closest to our sun is about 4 light years away. So 2.6 light years, there could easily be another star in this region. So what happens for a low mass star? At its very core, there usually isn't enough gravitational pressure to fuse heavy elements. So you'll have enough pressure to kind of force hydrogen and helium into nuclear fusion. And maybe you'll even get to the point where you can kind of force helium atoms to fuse into carbon atoms. But beyond that, there's kind of a higher requirement of energy to fuse heavier and heavier elements. And a small star, small, right? Like we're talking 1 to 5 solar masses, so it's still pretty big. But relative to other stars, what we call a low mass star. So for a low mass star, there just isn't enough gravitational pressure in the core to really force the fusion of heavier elements. So it starts to happen at the end of a star's lifetime, which could be 10 billion years. The core gets very, very dense as heavier and heavier elements accumulate in the core, but the outer layers of a star kind of still are filled with helium or hydrogen. So the core gets very dense. The outer layers are still relatively light, so that the gravitational pressure in the core is much, much, much higher relative to the outer layers. So what happens is the thermonuclear pressure inside the core of that star, from like the remaining nuclear reactions that occur, actually push the outer layers out. And just to go, if I can go back here, just to illustrate on this slide, you can imagine this difference in pressure kind of getting even greater and greater. The thermonuclear pressure in the core builds up so that it's so high, it overcomes the gravitational pressure in the layers right outside it. So you kind of have this explosion occur. And for a white dwarf, it's a fairly slow one, where the outer layers, all the mass of the outer layers is pushed outward, which creates this kind of nebulous ring, which is called a planetary nebula. And the remaining part inside is a white dwarf. So it's a very small, very hot stellar remnant that doesn't really have nuclear fusion going on. And it's usually going to be composed mostly of smaller elements like carbon and oxygen that are less dense. So that's the Ring Nebula. I just wanted to show, just because this is such a beautiful image, the Helix Nebula, right? This is something that's about 6 light years away. I put in here 5.74 light years. No, I'm sorry, that's its diameter. That's not its distance from us. So
Can you please say again, how many miles is a light year?
yeah, let me go back because just it's such a large number, I often don't remember. I had it here in terms of kilometers, actually, not miles. So 9.5 billion kilometers.
Which is what in miles? I'm sorry.
In miles, so a mile is a little bit larger than a kilometer, so this is probably going to be closer to 8 or 9 billion miles. The number that's kind of, is it 8 or 9, is less relevant to the scale that we're talking about, that this is billions of kilometers long. So when we say, what happened here? If we look at this and we say, okay, so this is 6 light years, right? Each of those light years is about 8 billion miles. So this is just like, what's 8 times 6? I can't do math in my head. What,
48.
Yeah, so 40, we're looking at 48 billion miles across, which you could think of it in terms of miles. But I feel like once you're at a number that's that large, it kind of loses its meaning. Like, I can't process a number like 48 billion. I've never seen 48 billion things, so I don't necessarily understand what does that mean. I can't visualize it because it's just too big. But if we kind of introduce this new unit of a light year, I can describe that distance in a smaller number like 5.74, and I can say, okay, well, that's a number I can understand, and the size that I'm really talking about is kind of contained in the unit of light years itself. So I don't have to kind of get distracted by that size of the thing.
Isn't it true there's 100 million stars in our galaxy and there's 100 million galaxies in the universe?
Oh, I'm gonna get there. There's quite. I'm hoping to get as far as galactic structure or structure of the universe. We'll see if time allows for that. But yeah, there's an incredible number of stars and galaxies. Just the size of the universe is incredible. Okay, so that's the Helix Nebula. And again, like you can kind of see in the middle, you can see that white dwarf remnants from the star that used to be there. And then this planetary nebula that kind of got shed and pushed outward. And there's a lot of stars in the foreground and background, but it looks like there could also be stars within the nebula itself. And that's part of the process of how new stars are born, right? Is you take that matter from dying stars, can create a new star.
So the universe is alive.
What do you mean?
It grows, it expands and decreases, so it's alive. Yes?
I think a biologist would disagree with that.
Yeah?
Yeah, I'm not a biologist, but I think that life, as defined biologically, involves kind of a little bit more than what is going on a cosmological structure. But I like that analogy of saying, like, it seems as though it's alive, right? Because there is so much change, there is so much going on. I should also point out, though, that this change is occurring over very, very long periods of time, right? So these changes, right, a planetary nebula forming, this is occurring over the course of millions of years.
Wow.
Right? A star's lifetime can be 10 billion years. For some of the shorter spans, like shorter-lived stars, even those live for millions of years. So these changes happen, but they're very, very slow. There are some that happen really fast, and those are what I would like to get to next.
Okay.
And that would be a type 2 supernova. So this is an event that can actually happen very quickly on an astronomical scale. So a type 2 supernova is what's going to happen with a really high mass star as it kind of dies. And I have here an image of one. It's called V838 Monocerotis. And the diameter here, you've kind of noticed I've shifted units again. I'm not even describing it in light years. This is in terms of astronomical units, right? Because this is a little more compact. So the distance here is 3.5 astronomical units. You'll notice that is something that could fit inside of our solar system. So a type 2 supernova it's very similar to what happens when a star dies and leaves behind a white dwarf. But in this case, it's going to happen with a very high mass star. So again, a high mass star, really we're talking anything that's over about 5 to 10 solar masses, but some of them can get very large. You can have some that are dozens. I mean, we know of stars that are at least 40 solar masses. I think some of the largest stars that have been found go up to 300 or even more. So there are some very high mass stars out there. So for this, gravitational pressures, again, it's creating very, very high pressures in the core. And at this time, because there's so much gravity pushing in, it actually is strong enough to cause the fusion of larger elements. So instead of fusion kind of stopping at carbon, it kind of continues. And this is where you get heavier elements in the universe. Like we have elements in the world, like, I wish I had put up a periodic table in these slides just to show. But if you guys are familiar with the periodic table, there are elements like gold and copper and xenon and things that are just larger, have a higher atomic mass. All of them, all of the elements larger than hydrogen are fused in the core of stars. It's really the only place where you have enough pressure to force that kind of fusion to occur. So this is where it's going to happen. All of those larger elements that we're familiar with, this is where they're being made, is in the cores of these supermassive stars. So generally, in a star like this, for the most part, fusion kind of is going to stop at iron. And I kind of just want to show this scale. This is a scale of nuclear binding energies, and this is what I find part of what I love about studying astronomy is you could be talking about something as big as a supernova, and then in order to describe it, you have to talk about something as small as an atomic nucleus to explain what's happening. So in a star like this is just a graph of nuclear binding energies showing how much energy it takes to fuse a certain atomic nucleus. And what's at the top, it says Fe, that's the atomic symbol for iron. Iron is really the most stable nucleus of all the elements. And once a star has fused iron in its core, there's very little other fusion that can take place. Obviously, there's some that happens because there are elements heavier than iron, but most of the fusion taking place is going to basically stop at iron. And iron, as you probably are aware, is very heavy and very dense. And that makes the core of this star even denser than the core of a white dwarf before it collapses. So the gravitational pressure becomes even more powerful. And because fusion can't occur, right, beforehand we had said that that balance of pressures, just to go back, I can go back to this slide, we said the balance of pressure here in the center caused nuclear fusion to occur. But now that we are at the point of the core has been converted to iron, there isn't really more fusion that can be done, right? Something new starts to happen, and all of that iron, all of those elements in the core of the star are pushed even closer and closer together, to the point that the electrons start to kind of overlap. Even the nuclei of the atoms may be forced to share the same space, and then two new pressures are going to occur. Right? You've got the electrostatic repulsion of electrons, which for the record is a lot stronger than gravity. I think a lot of people think gravity is very powerful, but if you think about it, like if you're standing on the floor, gravity is pulling you down, and what's keeping you up is the electrostatic repulsion of electrons on the surface of your feet and the floor. So it's just the repulsion of valence electrons is enough to overcome the force of gravity. So gravity is pretty weak relative to other fundamental forces. But we get to this point where the gravity is strong enough to start to overcome that electrostatic repulsion between electrons and protons. And it may even get to the point where there's another thing. If they're pushed too close together, in quantum mechanics, there's a principle called the Pauli exclusion principle, which states that two of the same particle can't exist in the same state, in the same place, right? So two electrons can't occupy the same state in the same orbital. It gets like, yeah, it gets very quantum mechanical very fast here. So at that point, once the electrostatic pressure is overcome, right, you now have what's called degeneracy pressure, is this pressure of, you can think of it as particles literally being kind of forced to occupy the same space, which, you know, they don't want to do. So at that point in time, once the pressure gets strong enough to overcome that degeneracy pressure in the core, what can happen is the core then collapses. So I'm going to skip, this will let me. And we are left with a neutron star. So the neutron degeneracy, kind of that force kind of keeping neutrons apart from each other, is overcome by the gravitational pressure in the core, and the core kind of collapses so that all the neutrons are pushed really, really, really close together, and the rest of the material kind of explodes outward, right? The electrons, the protons, which have a higher degeneracy threshold, so they're not necessarily pushed together. All of the outer layer, all the outer layers of the star can get pushed away by the force of that reaction occurring. And what's left is a small core that is so small and so dense.
This way.
It's on par with the size of Manhattan, right? So here's just an outline of Manhattan Island, and here is kind of a typical neutron star placed next to it. And just to illustrate, you know, I had compared the process of a planetary nebula occurring as taking maybe thousands of years, and the lifetime of a star taking billions or millions of years. This process of a neutron star collapsing, the core collapse occurs in a matter of seconds. And the shock wave moving out toward the edge of the star occurs in a matter of hours. So here's another kind of comparison of a neutron star over Chicago, where you can see this is, I got this, I believe, from the University of Maryland website. This is a radius of only 10 kilometers and a mass of 1.4 solar masses. So this is on par with the mass of the sun, and it's being crushed into a space that's that dense. One of the things that happens often with neutron stars is people love to do density comparisons and be like, oh, 1 teaspoon of neutron star is equivalent to, and then say something incredibly huge, like the mass of all humans. So they're very, very, very dense bodies. And just to kind of illustrate, again, visually, how large these things can be, this is like a typical neutron star. This would be like the largest one. So they don't get very big. I mean, for a neutron star, past a certain threshold, something else is going to happen, right? The pressure is too strong. Past a certain threshold, instead of kind of compacting into a neutron star on the core, it'll get even denser. But take those and then compare them to like the Earth. So this is a neutron star. This is a white dwarf that we talked about before. This is planet Earth. And just to kind of go back and illustrate, when we compared the size of planet Earth to the sun, go back all the way to the beginning, right? How large the sun was relative to Earth, and then take all of that mass, and let's go back to where we are now, and just imagine compacting it into that much space. Okay, so the density here is just absolutely beyond belief. There are, these tend to be pretty far away, so I've just shown a couple of what are artists' renditions, and I want to be very clear about when I'm showing an artist rendition versus when I'm showing like an actual image, right? So this, I mean, that's an image of Earth, but even something like this is an artist's rendition. These are not actual images of a neutron star, in part because of what we see in these artists' renditions. There's a lot of material that surrounds them. You usually aren't going to find something with that powerful of gravitational attraction just floating around by itself in space. It's going to be surrounded by other matter that it's attracted. And here it even shows kind of the magnetic field lines and some ejection jets. If you ever hear of weird names of stars, like someone saying like, oh, a pulsar, a magnetar, a quasar, like all those cool names of like exotic objects, those are usually referring to different types of neutron stars because they can get very weird. Oh, I forgot I put this in here. This is a composite false color image from an X-ray observatory, just showing kind of how these false images are created. Is they'll sometimes kind of do this false color image in a lot of different spectral bands and then overlap them. But this is another another neutron star, kind of, well, it's the supernova remnant. So you'll have a neutron star in the middle, and then all of this kind of exploded stellar material surrounding it. And it's pretty cool. But you wouldn't see that if you were actually looking at it, right? This is what it looks like in the visible spectrum. So it's not as impressive, which is why, you know, observational astronomy nowadays has had to take leaps and bounds in terms of the types of light that we look at. If we were looking at this just in visual light, this is all we would see, you know. We kind of have to look at it in terms of in X-ray wavelengths, and then we start to see some of the real structure and material involved there. Okay, what happened here? Last thing is, so we talked about what happens once degeneracy pressure is kind of overcome in the core of a star, and that creates a neutron star. If a star is massive enough, then the degeneracy pressure of the neutrons as well as the electrons and protons will be overcome as well. So you can end up with an even more dense compacting of the core, and that results in a black hole. So you may have seen kind of this, and I don't know, maybe you've seen it, maybe you haven't, this equation describing the Schwarzschild radius. It describes the radius of basically how small something would have to be to become a black hole. And you can just calculate. You can take any mass and put it into this equation and find out how small would that have to be to become a black hole. So like I took Earth, and Earth would have to become 1/3 of an inch in radius. The sun would have to become 1.8 miles in radius to become a black hole. And then I thought, why not compare this with a real black hole, something like Sagittarius A star, which is a black hole in the center of the Milky Way galaxy where we live. And that would have a Schwarzschild radius of 12 million kilometers. So just to kind of compare, the sun has a radius of 1.8 miles, and this is 12 million kilometers. That's close to 10 million miles. Like it's just another level. You can kind of imagine like how large something would have to be in order for its Schwarzschild radius to be that big And it's estimated at between 500,000 to up to 4 million solar masses. So this is a very massive object. I wanted to give you kind of a visual comparison of what that looks like. So for planet Earth, this diameter, that kind of black hole radius, I took here, this is just an image of like standard marble sizes. This is how big the Earth would have to be. Earth would kind of be reduced if it's, you know, if its diameter, if its radius is 9 millimeters, its diameter is going to be 18 millimeters. So it would be about the size of a very large marble to become a black hole, right? The sun, I'm taking back to this image of like a neutron star next to Manhattan. That's about how big the sun would have to be to become a black hole. And then looking at an actual black hole, right? Sagittarius A star, it would have to have a radius of that diameter of 12 million kilometers, right? And that is the size of an actual star, right? There's a star, you know, kind of our local galactic neighborhood that's called Pollux, and it's about that size. So this is just vastly, vastly different. One thing I'll skip because we're already kind of, it's 2:40 and I wanted to leave some time for questions. I'll kind of skip this slide. This is an artist's rendition of what a black hole might look like, kind of showing the event horizon, all of these different phenomena that occur around it, right? You're going to have a lot of material is going to be attracted to this because it has a very, very, very deep gravity well. And a lot of interesting things can happen just in the material surrounding a black hole. But what I think is even cooler is this actual image of a black hole, which is, and this was released in April 2019. So this was just over a year ago. We got the first real image of an actual black hole. And this took years, like years of observation, of software development just to produce these images. And they're actually the software engineer who worked on this. She has a very interesting TED Talk about it and all the work that went in. But this kind of shows this yellow and red area really is showing not the black hole itself, but what's called the accretion disk. All of the matter surrounding it that gets very, very hot and energetic and starts to glow. And then this dark area in the middle is what is referred to as the shadow of the black hole. It's kind of a relativistic visual effect where we can kind of see the impact of the black hole indirectly. This is probably one of the most incredible images I think that has ever been taken, just because of, you know, for how much work went into this. And for a long time, I think people really believed that it wasn't going to be possible to directly image a black hole, especially because some of the ones that we can see are in distant galaxies. They're not that close to us. So this was really, really incredible when this happened. And it was just over a year ago. So this is new stuff. It's 2:44. Just to kind of, I'll real quick go through the rest. We talked about stars. Someone before mentioned like the galaxies and the scale of the universe itself. So I wanted to show, I'll real quickly run through this. This is the Milky Way galaxy, and this is, you know, an artist's rendition. Obviously, we don't have a camera that's floating above the galaxy taking pictures. So this is an artist's rendition. And we're talking, you know, from one end of the galaxy to the other, about 100,000 light years, right? So that's an incredible scale. We can then look at kind of comparing it with other galaxies, the Milky Way versus Andromeda. Oh, this is an interesting slide I put in. This is how Andromeda would appear in the night sky if it were bright enough to see. Very big, bigger than the moon. Just comparing it to larger and larger galaxies, this one being 6 million light years across. I think this is the largest galaxy that has been discovered to date. But then when you want to look at like the larger scale of the universe, right, you can look at the local galactic group, right? The Milky Way is right here, and here's a bunch of other galaxies. And at this point, right, we are going to be measuring the distance here in terms of kiloparsecs at least. Like it's crazy, the distances that we could talk about. They're very, very far away from each other. even that. Here's the local group right in the middle, and you can kind of look at these larger structures. Right here you've got the Virgo supercluster in this area, and other superclusters of galaxies, kind of creating what is now the largest known structure. Laniakea is this large galactic structure in the local universe. Local, kind of a relative term. And another depiction of Laniakea. This was released a couple years ago. Kind of a web image, kind of showing. So this is more just showing the positions of some of the major galaxies and the major groups of galaxies within this region. And this is kind of showing the web of kind of how they are moving toward each other or away from each other. This red dot being the location of the Milky Way. And you can kind of see that there's this tendency of like along these, what looks like lights in this image that really represents matter, right? And there's this kind of interesting tendency for the matter to kind of form these filaments and congregate. And then you can look even further at the greater galactic structure, and you get to what's called the cosmic web, where you have just these incredible, it almost looks like a neuron structure of matter, all coming together in this weird web-like way. So that brings us all the way from Earth to the size of the universe. And kind of to summarize that, I found these two images kind of progressing on a logarithmic scale of size, going from Earth, right? And this one I think is really, really cool. This shows starting on Earth, kind of comparing logarithmically distances that occur. So logarithmically meaning instead of distances being the same, it's like as you progress, distances multiply by a factor of 10, right? So you've got like Earth and the moon and the sun, and you can kind of you leave the solar system, you get to the Oort cloud, distant galaxies, and you can kind of see all the way out here, kind of that structure of the universe itself, all the way out to the edge of the observable universe, which is very large. So thank you for listening. And I think it's about 2:50 now, and it was, or I guess in my time it's 2:50. In Memphis it's 1:50 because I'm in a different time zone. And I was told that you guys have another program you may want to go to in about 10 minutes, but I'm happy to take any questions if you have them.
I was wondering whether you could see a nuclear star because it was so dense. Does that create a lot of heat or light, or it's just so small that you can't see it?
Yeah, so for a neutron star, I'll go back a little bit. When we look at something like the Milky Way galaxy, I'll just take a step back. We can't always see things directly, but we can sometimes see their effects, right? So this bulge, this very bright area in the center of the Milky Way, has a black hole in the center of it, right? So we can't see the black hole, but we can see all the matter that's around it, and we can kind of infer, based on the forces, how massive an object has to be at the center of it, right? So we can't always observe things directly, but for something like a neutron star, and I'll go back to where I talked about like the different weird names of neutron stars, like a pulsar. This is something that we can see because neutron stars, one of the interesting things that happens with them is first of all, they spin at very, very high speeds. They can do like tens of thousands of rotations per second. And as they accrete matter, what can happen is that the matter kind of falls along the magnetic field lines because they frequently also have very, very powerful magnetic fields. And that produces these ejection lines that are in this artist's rendition, showing matter kind of being shot out, matter and light, honestly, being shot out of the neutron star as it's being kind of pulled in and then kind of focused and released by the forces around it. So what happens is as it spins, we can kind of see, if you can imagine like the light, it's like a flashlight spinning. You could kind of see changes in the brightness, right? So you can measure the period and you can measure the brightness and you can see like, oh, it's like spinning around, and when it's facing us, we're seeing something very bright, and when it's facing away from us, it looks a lot more dim. So even though we can't necessarily image them directly, we can see these really interesting effects. Also, part of the reason why they're difficult to image directly is, as we pointed out, they're usually surrounded by a large, dense cloud of other matter, right? So we may have to find the specific wavelength, like the gamma rays, for instance. If we were measuring just the gamma rays, maybe we'd see through all this cloud of other matter to the star itself. The other reason why it can be really difficult to get an image directly of a star like this is that they're fairly rare. Black holes and neutron stars form from the deaths of very, very massive stars. And those types of stars are a lot less common. Most stars are approximately within the range of the mass of our sun. So these being less common, they also tend to be very far away from us, which makes it also a little more difficult to image. In fact, I don't know if there is any star that we've directly imaged the surface of other than the sun itself. Just because they're really far away, and we can get, like, you can see stars, obviously. You can look out in the night sky, you can see them, but most of the images we're gonna get are not gonna be like those surface images that you see of the sun, where you can really see like texture and events occurring. Yeah, well, thank you for that question, Rabbi Finkelstein. Any other questions from anybody else?
Thank you. That was very enjoyable.
You're welcome.
And here's another question. In our own night sky, even here in Memphis, we can sometimes see Orion, and inside it there's a nebulous. Where does that fit into? Is that just a bunch of stars? How does that fit into?
So a nebula usually is going to be, a nebula is usually a region of kind of old stellar death, as it were, like as other stars die and kind of explode. We saw that for neutron stars and black holes, and even for white dwarfs, they leave behind this shell of matter. So if there's an old generation of stars that have kind of all died out, they've left behind all of that matter there. So it remains as this large nebular structure. So yeah, that's a very good question. A lot of the times we even find in those structures, in those large nebulae, other stars will start forming, right? All that matter will start to accrete again and kind of collapse, and you may get new stars forming in those areas.
Hey, Gabby, I really enjoyed that.
Thank you.